And I've got two real people who have their webcams on. I am happy. So happy I'll do this. Didn't know I could be a wild and crazy guy. All right, let's get started. Good afternoon, everybody. Welcome to a wonderful Wednesday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. You notice my fingers make my eyes go large? But anyways, I'm in a good mood. A lot of good things have been happening to me, including I was looking for a new, actually a lawyer of mine had retired a while ago and I hadn't found a new one. And I just found one earlier today. So I'm happy for that. Happy for my blueberry tea and happy to start talking about organic chemistry. All right, but first, an important announcement from me, Dr. White. And that is, you people have been so nice to me this semester. Why don't you take Monday off? We'll just skip class and my office hour. Just take Monday off. If you don't know, it's Labor Day and we won't have classes. We won't have office hour. I won't have office hour. Now, another thing about office hour, and I'd like to ask everybody, is the time I have my office hours good for you? If you can think of a better one later Monday afternoon or evening, not too late, email me in because I've got the power. Yes, I have the power to change my office hours. We're on Zoom. If we were face to face, I'd have it right after class for an hour and 15 minutes. But since we're not face to face, we're on Zoom, I can change it. So email me, let me know if there's a better time on Monday and Wednesdays, and maybe even Tuesdays. But I'd like to keep it Monday and Wednesday. It can't be in the morning because I teach from 9 to 11 Monday and Wednesday on Zoom at College of DuPage. So I'm not going to have my office hour and teach at the same time. How do you like that? Well, as you can see, I'm really in a good mood. All right, let's get to work. Let's talk about today's game plan. First of all, I'm going to go through the problem set for chapter 2. Do I go through every problem? No, I'll go through some of them. If you'd like me to go through a problem I haven't gone through, ask. Remember, in my class, there's no such thing as a dumb question. Not only in my class, but in my universe, my world, outside of my class. And after the problem set, we'll go back to the alkenes, double bonds, and alkynes chapter. I don't even know the chapters. I go by functional groups. We'll do some of that, and then we'll go through today's lab. And that's our game plan. Now, normally we do about 50 minutes of lecture, take a break, then I do the lab and let you go. But because Monday I'm going to lose 3 hours last week and this today, I'll go a little longer. And that way we'll keep on schedule in spite of Labor Day. By the way, when I'm face to face, I do it the same way. Now, I just remembered I forgot to open something. And now it's open, so let's get to work. All right, everybody see alkanes practice problems on your screen. All right, first of all, and I'll put it out before next Wednesday, I'll put out an announcement and an email. I do this for every test and I'll do it for the final 2. I'll tell you how many pages, how many points, and how many points on each area. Now, for organic chemistry, this course, I break down the test into 3 areas. One is general knowledge, the second one is nomenclature, and the third one is reactions. And what general knowledge? Well, I might ask how many bonds to carbon, How many bonds to carbon? 4. Or other things that are just general knowledge. Now, nomenclature, there are two main areas. One is, here's the molecule, give the IUPAC name. The other is, here's the name, draw the molecule. And the final reactions, give the product or products for the following reaction. So let's get to work. Now here, in the first one, since you're starting out new, I made it easy for you. I didn't even put down hydrogens. How many carbons are in the longest chain? That means carbons bond together, connect together like a chain. And if you look at B, count across 1, 2, 3, 4, 5, 6. Remember, the math skills of my class are real hard. Right now, I expect you all know how to count to 10. And you also know what numbers are smaller and larger from 1 to 10. Now, if we look at D, there are two different chains. I can start here 1, 2, 3, 4. I can go across 5, 6, or I can go from 4 down 5, 6. And notice there's another chain that I didn't mention, 1, 2, 3, 4, 5. But the longest chain would be 6. Now, if we look at F, Dr. White got sneaky, and we have what's the longest chain? Well, if I count it across 1, 2, 3, 4, 5, 6, that's one chain. But the longest chain, this carbon 1, is bond to 2, bond to 3, bond to 4. Then you come down here. That's still connected. Remember, if you've ever played with a chain or had a chain like this around your neck, it's gold in case you're looking. But anyways, it can bend every different way, and carbon atoms can do that too. So I have 4, come down here to 5, 6, 7, 8, 9. Now there's one more chain I didn't show you, but I'll use the cursor. 1, 2, 3, 4, 5, 6, 7, 8. So you had 6, 8, 9. What's the largest number? Hopefully you all pick 9. All right, now let's go to any questions on longest chain. All right, next one, give the IUPAC name for the following molecule. Well, how do you do that? An IUPAC, which I'll never ask on tests, but I think it's just cool to say, International Union of Pure Applied Chemistry, but that's the official name. Whatever you see on my test, IUPAC, that's the official name. Later in the semester, some of the chapters, I'll teach you common names also. Those are names that have been used for eons, long before IUPAC became reality and their rules, and they're still used to this day. All right, now here, A, how do we find out what's the name? How many carbons? 1, 2, 3 in the longest chain. You know the table, 1 through 10 carbons, 3 carbons, propane. Next one. What's the longest chain here? 6, 1, 2, 3, 4, 5, 6. Same table, 6 carbons, hexane. This is 9, nonane. Now I have it here, or I'm not going to use the bracket or parentheses with a number until we get, I'd say week 15, where I talk about molecules that have 18 carbons in it. Instead of you watching me for a minute or so writing CH2 16 times, I will use parentheses. But until then, I'll do it always this way, which it means on the test. Now, let's look at D. Now, D has a substituent we call an alkyl group or branching. You don't have just one long chain, that's it. So now you have to figure out what is the longest chain. In this case, 1, 2, 3, 4, and that's butane. And then, it's your old friend CH3, the methyl group. And you put in front of that the name methyl. And I shouldn't be lazy. So you should know the key alkyl groups. One carbon bonded to a chain or a ring is called a methyl group. Two carbons, the N carbon, ethyl group. Three carbons, there's two possibilities. When it's the N carbon, it's N-propyl. When it's to the middle of three carbons, it's called isopropyl. Then for four carbons, you have actually three choices. One of them, I'll be honest, in my professional career, I've never used, so I'm not going to teach you. See how mean I am? But anyways, four carbons in a straight chain, the N carbon bonded to a chain or a ring is N-butyl. And one of my favorites, I like isopropyl too, all of my life. But there's something really neat about three carbons bonded to the center one and the center one bonded to a ring or a chain. That's called tert-butyl. And starting next week, I'm going to be a lazy organic chemist and just call it T-butyl. On a test, you can write it either way. And you should know this chart just like you know your first name. I'm assuming you all know your first name like that. Oops, like that, which I know mine, and hopefully you know yours. And while we're here, let me open up one more thing. And hopefully you've learned this chart. You know the name and the number of carbons. Methane, 1 carbon, heptane, 7, octane, 8. Anybody think of organic chemistry and octane when you go into a gas station? You should. And decane, 10. You should know these like you know your first name. And I'm assuming everybody knows their own first name like that. That's not what I want. All right, so CH3 methyl group, and then you have to put a number. What carbon is it on? And you start always from the end of the chain. Common mistake students make on test one. Well, methyl group on this carbon, let's call it 1. No, it has to be the ends of the chain. Either this end or this end has to be 1. And you number it from the side that gives the alkyl groups the lowest numbers. If I go this side, it's on carbon 2. If I go on this side, it would be 3. Hopefully you all agree 2 is less than 3. So it's 2-methylbutane. Now I put in E just to show you molecules like you and I move in space and rotate. If I were to say, oh, look what I have here. I say, close your eyes. While you close your eyes, I do this. I say, oh, look, it's something new. You just look at me and say, come on. You just rotate your hand. Well, that's all I did when I went from D to E. And notice it also has the same IUPAC name. And that's the beauty of IUPAC. Every molecule has an individual name. No two different molecules have the same name. And if you draw a molecule either way, like D and E, guess what? You still come up with the same name. Now, if we look at G and F is similar, we have what's the longest chain. In this case, I put it across 9 carbons, no name that goes at the end. We have 2 groups, a methyl group on carbon 2 and 3 carbons, center carbons of chain, isopropyl. Now, the way I write it, I'm always going to try and be correct. I might make a mistake because I'm human and I don't walk on water unless it's frozen. Even then, I stay off it. But here, I will not, don't tell anybody I'm being nice, but I will not hold you on my test to the IUPAC alphabet rule. And that is the substituent with the higher alphabetical priority, closer to the beginning of the alphabet, goes first, and then after that you follow the order. And prefixes are not considered for alphabetizing. So this is an M, this is a P. Most students say, why don't you call it I? Well, that's the rule. And M comes before P, so it's 2-methyl-4-isopropyl. But on a test, if you wrote 4-isopropyl 2-methyl-nonane, I would give you correct answer, full points. All right, now let's look at H. H is very important. This is a ring. You count each bend in a line, which is a carbon. You don't show hydrogens on a ring. Remember, there are 4 bonds to carbon. And 6 carbons. You've learned this table. Hexane. But it's a ring. So we use the prefix cyclohexane. Pay attention. Common mistake on test 1. Student will write down hexane, and I'll give them 0 points. And they say, well, don't I get partial? No, hexane straight. This is a ring. You got it wrong. So remember, when you have a ring, it's a prefix cyclo and then the alkane name. So this is actually a cycloalkane, cyclohexane. Now, when you have one substituent on a ring and nothing else, you don't use numbers, because that substituent always is going to be on carbon 1. It has to. Everybody knows that. So if everybody knows that, we don't put a number. So here I have a ring, cyclohexane, and again, 3 carbons, center 1, isopropyl. So that would be isopropyl cyclohexane. If you put a number, I'll take off a point. Now here we have a ring. How many carbons? 1, 2, 3, 4, 5. Pentane, it's a ring. Don't forget the cyclo. Cyclopentane. Now we have my favorite, a T-butyl group, tert-butyl. We have an ethyl. Now the IUPAC rule is 1, you give the alkyl group or substituent with the highest alphabetical priority the lowest number, 1. I'm not going to hold you to that number rule. And so there are 4 possible answers you could give, but I will do the correct IUPAC way. So if this is 1, this is on 2. You always number the direction to give the alkyl groups the lowest number. Again, if this is 1, that has to be 2. Because we want the other way, it'd be 2, 3, 4, 5. And 2 is less than 5. So I have cyclopentane, I have 1 tert-butyl, and on carbon 2, 2 carbons, ethyl group, 2 carbons, ethyl group. So it'd be 1 tert-butyl, 2 ethyl, cyclopentane. Now, if you'd put the 2 ethyl first, I'd mark it correct. If you had switched the numbers, even though it's not correct per the IUPAC rules, I'll give it to you. And finally, if you have the numbers and names switched, I would also give it to you. But what I always try and do is correctly name it. Now, as I said earlier, there are 2 types of nomenclature question on test 1, and they'll be on test 2, 3, 4 in the final. And one is, we just did, give the IUPAC name for the following molecules. Can you guys keep a secret? Here's the secret. After test 1, you'll understand why I call them practice problems. After test 1, you'll understand why I call them practice problems. Any of you have ever seen any Monty Python programs? The English, you should. And there's this one of their famous skits, and a key part of it, one guy says to the other, wink, wink. Oh, hint, hint, wink, wink, say no more. My left, right, this wink. Hint, hint, wink, wink, say no more. Watch for it. It's on YouTube. But anyways, the other type of nomenclature question is draw the condensed structure. Condensed means you don't put a bonds for every carbon hydrogen bond, but you can put them between the carbons, which I usually do, and draw the structures. And methane, one carbon, and now you have to put in the hydrogens. Remember, there are 4 bonds to carbon. Hold on, let me fix my finger there. 4 bonds to carbon, and you know how to do it. Let's look at butane. Anybody remember see those little lighters with the liquid in it for cigarettes? Thank God I gave up cigarette smoking eons, decades ago. When I was younger, I was a heavy smoker. I could tell you how many cigarettes I had to have in my pocket, because back then, or my shirt pocket, back then you could smoke on planes. How many cigarettes to go from Chicago here airport to major airports in the States, United States, and the world. And I still remember Detroit was a 2-cigarette, LAX, Los Angeles was about 8, and Amsterdam and Manchester and London were all almost a pack and a half. Why do I remember that? Don't know, but I remember it. But the little liquid, the liquid in the lighters is butane. How do you know what to draw? Butane, 4 carbons, straight chain. So I have my 4 carbons. Remember, there are 4 bonds to carbon. This first carbon has 1 bond. 4 minus 1 is 3. The second one has bond here, 2 bonds to these 2 carbons, adjacent carbons. Adjacent means next to it. And 4 minus 2 is 2. And that's how you figure out the hydrogens. Now, let's look at F. How do you do this? Well, you start from the right, move left. The longest chain, hexane, 6 carbons, 1, 2, 3, 4, 5, 6. And then methyl, oh, I know that's CH, 3. Now, the prefix di means 2, tri means 3, but di, and I forgot the dash there, don't look. But anyways, di means 2 methyl groups and a number in front, not 1, but 2, because since it's di, you need 2 numbers, and I have them, iron carbons 2 and 3. So if I start here 1, this would be 2, this would be 3. And here we go. Now you could have started from this side, made this 2 and 3, which most of you wouldn't do. I might, but all you're doing is rotating the molecule. And I made a mistake on the name. I corrected it, it's totally wrong. Should be 1-tert-butyl 2-ethyl cyclopentane, but anyways, cyclobutane, butane 4 carbons, cyclo, it's a ring. You call that a square. No, I call that a ring. I'm an organic chemist. Now, if we go here, cyclopentane. Now, there are many ways of drawing this. I drew it this way to confuse you or remind you, but 1 carbon has a T-butyl group and the second carbon has an ethyl group. And just to show you the way most of you would probably do 1-tert-butyl 2-ethyl cyclopentane. Cyclopentane. Ooh, I'm having a good ring drawing day. Yay. Must be why I'm happy. And T-butyl. And this is 1. Most of you are going to go clockwise. 2 is the ethyl group. And this is how most of you probably wrote it. Remember the answers you see when I show, and you can also go back and look at the video too, are available. The files are available on D2L, and the videos obviously are on my YouTube channel, which a lot of you are watching, making me a YouTube star. Yay! Now, if you notice in J, I have 2,3,5 trimethyl octane, octane, 8 carbons, 8 across, and on carbons 2, 3, and 5, tri means 3, methyl is CH3, and this is how it be: 2, 1, 2, 3, 4, 5. So 2, 3, and 5. All right, now, when it comes to the test, I will ask you the reaction product or products for the following reactions. And here, how do you do this? Well, I got lazy and I didn't do the what I should have. So let's go to my whiteboard. Oops, getting ahead of myself. Now, the question is, what are the product or products for this reaction? How do you do that? Well, this is different, oxygen gas. Remember, A and B are the starting materials. If you've come from industry like I have, and more likely that's what I'll call them. They're at the base of the arrow, or you might also call them reactants. At the head of the arrow, whatever's there is called a product or products if they're more than one. So if you're trying to find the products, you look at the starting materials. One is oxygen. Then we look at this and say, what is that? And you look for what's different, or it's just carbon-carbon single bonds and hydrogens, and that's an alkane. It could have been a cycloalkane. And this is called combustion, which happens in your car engine. And that's what gasoline undergoes, because gasoline is 50% of the weight of gasoline is alkanes. Well, what you get is carbon dioxide plus water plus heat, but that's not considered a chemical product. And therefore, if I have propane, which is an alkane, and react it with oxygen, I will get carbon dioxide and water. As I mentioned in class before, in this class, you will not ever be asked to balance equations. Most of the times, organic chemists, when I'm talking, we don't balance equation. The only time you do, if you need to calculate what's called charge weights. How much of this chemical do you react with that chemical to make a certain amount of the product, which I have done both for the lab and chemical plants writing. It's called procedures. The largest procedure I've ever written, I've done it a number of times. One company I worked at, the reaction had final product 180,000 pounds. That's a lot of chemicals to deal with, a lot of money too. Just to give you a little knowledge of the real world, how many of you have ever seen the vehicle that delivers gasoline to gas station? In a long vehicle, we call that a tank wagon. And a tank wagon in the United States, well, actually in the whole world, is standardized. 40,000 pounds, 5,000 gallons. And so if I'm saying I've done reactions with 180,000 pounds final product, you're talking about 4.5 of those tank wagons you make at one shot. That's a lot of fun. It's a lot of also pressure, because it's a lot of money and you don't want to ever mess up. Also, you could realistically, if you mess up, you can kill people, which thank God never happened to me. Oh, I know what I should do before. And this to show you. And here's a picture right here. And that's a tank wagon. Up on top here, you can inspect things, and you can, bottom here, you can't see it, is where you get, or sometimes at the end, that's how you get chemicals out. And one company, this one doesn't have it on this side. On the other side, there's a ladder. This is called a rear row car, tank car, or tanker. Those are different sizes, up to 250,000 or 10,000 gallons or more. And you climb up there, and before you ship, you look in there to make sure it's clean. And it's not fun climbing that ladder in a snowstorm in the middle of winter in Chicago. Been there, done that. Now, also had people work for me, but when it was that dangerous, I figured I better do it, not let someone else possibly get hurt. All right, let's get back to the problem set. So, one other thing I should mention. What I have here, this is called the general reaction. It's general because any alkane, any cycloalkane, when you do that reaction, will give you carbon dioxide and water. You should start memorizing and know these alkanes. Now, if you remember the first day of class, I talked about writing things down 5 times and saying it. And it works a lot better for most of my students and me when I was a student than flashcards. Flashcards never worked for me. Doing repetition worked real good. Now, on a test, some of my best students, every reaction problem where they have to give the products, they always wrote the general reaction. Some of my best students always wrote the general reaction. But then again, some of my best students never wrote the general reaction, but they had it in their brain. They knew it. Listen carefully. Every problem I do, I always write the general reaction underneath. Do you have to on a test? No. But that's what I'll do because it helps you learn those. Now, if we go back to the problem set, B is an alkane oxygen. Guess what? It gives the same thing, CO2 and water. And C is also a cycloalkane, and that reacts with oxygen to give CO2 and water. So guess what you get? CO2 and water. CO2, carbon dioxide, water, H2O. And we're done. Now, one of the things students always ask me is, Dr. White, are there other problems I could practice on? And I say, well, create your own, come to my office hour or see me after class on Zoom, and I'll check if your answers are correct. How do I make my own? Well, if we're doing these, I said, well, pick an alkane between 1 and 10. I picked 3, react with oxygen. Pick another one, 1 and 10. 8, pick a ring. So that's how you'll do it. And during the semester, I'll teach you more how to do your own practice problems if you need more, and show them to me, and I'll tell you if they're right or not. Any questions on the material from alkanes or cycloalkanes? Well, I have a question. Did anybody happen to turn on their gas stove and think that's methane? That's an alkane? Do you happen to either you did or someone else use a barbecue and we're cooking food on there? Do you think the gas, the material in the white tank that you burn to cook your food, that's propane? That's an alkane? Do you happen to drive by a gas station and think, ooh, gasoline, half the weight That's an alkane. Remember, organic chemistry is all around you. I stole that from SpongeBob. But it won't hurt for you to think about it when you're not in my lecture or on Zoom. Think about it. It's everywhere. By the way, Vaseline's alkanes, baby oils, alkanes, and if you're burning a candle, half the weight of the candle is an alkane called paraffin wax. All right, since there's no questions, I'm going to close this. All right, everybody see addition reactions on your screen. Thank you. Zoom, I do that because Zoom tells me you can see it, and sometimes students can't. It's a bug in Zoom sometimes that happens. All right, now we went through nomenclature, double bonds and triple bonds, and I'll go more once we finish the chapter. We'll do the practice problems like I just did for alkanes and cycloalkanes. We'll do the practice problems for alkenes and alkenes and alkynes. Now, let's get to the fun part of organic chemistry. Nomenclature is important, but the reactions are fun. And the first reaction I'd like to teach you that's better than just combustion are alkanes can undergo what's called an addition reaction. This on the screen, you don't have to write down. Now, we have a double bond. And a double bond contains this, you should know, one pi bond and one sigma bond. My Greek letters are awful today. That's better, a sigma bond. And why do I have the number 2 there? Don't know. One pi bond, one sigma. And that makes up a double bond. Now, sigma bonds, you don't break. But pi bonds, I can break like that and have a lot of fun. Now, the first type of reaction is called an addition reaction. Now, let me teach you something else I'll be using throughout the semester. In math, I'm sure you've all seen an equation like this: x plus y equals 50. And what can x be? What can y be? Different numbers. That's called a variable. Well, in organic chemistry, to show any type of molecule that has carbohydrates in it, we'll use the letter R. About a year and a half ago, I spent about an hour on a Saturday afternoon when I had some extra time, and I could not find who came up with using that. I just couldn't. But when I learned organic chemistry, it was being used. I don't know how long it's been used. I think the main reason someone picked R is if you look at the periodic table, there's no element with just the letter R. So if you have a double bond, you react it with something, AB, you break the pi bond, and each carbon of the double bond, I have here, and I shouldn't have, my software, there's a carbon there and there, gets part of this A and B. And you're adding to the double bond. Notice you break the pi bond, and it's no longer there. There's only a sigma bond. And that's an addition reaction. Now, this is very just an overview. This is not even what I call a general reaction. Now, this is something important, and I'll be reminding you this over and over again. In this class, carbon-carbon single bonds, also known as sigma bonds, are almost never broken. The only exceptions I can think of real quick are when you burn something, which I just showed you, combustion, or a reaction I'm not going to teach in this class, when you react a double bond with ozone. O3 is ozone. And by the way, I worked with ozone, doing research with it when I was a postdoctoral fellow at University of Illinois Chicago campus. Circle, as we used to call it, or they used to call it, I still do. But other than that, watch closely. Do you break carbon-carbon single bonds? No. I'll do that again in slow motion. Do you break carbon-carbon single bonds? No. Oh, that is. Anyways, you don't. Remember that. That's going to be your friend. When you take tests, two friends you're always going to have. One is, how many bonds to carbon? 4. The other friend is, do you break carbon-carbon single bonds? No. Those will be your friends. And over the next couple of weeks, I'm going to be brainwashing you to remember that. 4 bonds to carbon. Do you break carbon-carbon single bonds? No. So let's get back to work. And now it's time for our first really important, really good reaction. And that's called hydrogenation. Now, I will not, or I will never ask on a test, what's the name of a reaction? But I will use them in class because that's how we talk about them. Now, what is hydrogenation? It's the addition of hydrogen. I really should have your hydrogen gas to an alkene. What's an alkene? A double bond. Now, you need a catalyst. And the catalyst we use for this is platinum, palladium, or nickel. Now, what is a catalyst? It's something that makes a reaction go quicker. And it does that, and I'll never ask it, by lowering the activation energy. Why quicker? Well, if you didn't have a catalyst and you tried reacting a double bond with hydrogen, you can come back in a couple of months and not much will happen. When you use a catalyst at elevated temperature, about 140 degrees C, it's done in 4 hours. How do I know that? Well, I worked for companies that did this, hydrogenations. I did research in that area, and I've also managed reactions in a chemical plant with hydrogenations. So this is something I know. Now here I have it one way, and after I did these slides, wow, a while ago, everybody see there, 2014? Well, the copyright's still good. A better way to think of this is, in general, any molecule with a double bond, if you react it with hydrogen and a catalyst, where the catalyst can be platinum, palladium, or, hold on, I want to use cursive, and some of you may not read cursive. My other class, nobody can, or nickel. And what happens is, remember, there's 1 pi bond, 1 sigma bond. You break the pi bond, this is an addition reaction, and each carbon of the double bond gets a hydrogen. Again, this is a general reaction, and this you should know. And this can be said about every general reaction I'll teach you this semester. And you should know this, and you need to memorize it. There's no two things about it. Now, a number of years ago, and I don't know if it was accurate, but I think it was, one of my Chem 170 students counted at the end of the semester how many of these general reactions I taught, and it was about 52. You say, oh no, 52. Well, I personally know about 350, 400 general reactions, but I got a PhD in synthetic organic. That's I'm expected to know those. All right, now let's take a look at how you use this. Oops. All right, come on. Let's try this again. There we go. Now, certain part of my test, I'll write the question like this, because organic chemists are very biased. We don't like inorganic chemistry. So now one thing, and I'm running out of time here, let me show you something over here. Organic chemists can write A plus B goes to C. We can also, because we're lazy, write like this. And it's the same thing. And you can also put other things under the arrow. So this molecule reacting with hydrogen nickel catalyst to make something. Now, if I look at the clock, it's time for our break. So I'm going to do a cliffhanger on you. We'll come back in 5 minutes and we'll continue on with this material. So you'll just have to wait to see what happens in this reaction. I'll be right back, and hopefully you will too. See you in 5. Time to get going. All right, everybody back. Now we were talking about hydrogenation. And the following is the type of problem you should know how to do. And the question is, give the organic product or products for the following reaction. Or I could say for the following reaction. And here we have A. This molecule plus hydrogen, Ni is nickel. Well, how do you do that? From now on, whenever you look at an organic molecule, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that, or like that. And I love my little whistles. But anyways, what's different? Oh, look, a double bond. And as soon as I see that and there's nothing else different, the only thing I think of is I've got a double bond. What am I reacting with? Hydrogen. What's nickel? A catalyst. And remember, the catalyst can be platinum, palladium, or in this case, it is nickel. And what happens? Remember, there's one pi bond, one sigma bond. Do you break pi bonds? Of course. So I'm going to break the pi bond, but notice the line, one line is left there, sigma bonds. Because do you break carbon-carbon single bonds? No. So what happens? Each one gets a hydrogen. Each carbon of the double bond gets a hydrogen. So do you break carbon-carbon single bonds? No. So therefore, I have 3 carbons. Everybody see that? I started with 3. I better end up with 3. Which carbons are of the double bond? These. Notice I broke one of the bonds, the pi bond, because that's what my general reaction tells me to do. And each carbon of the double bond, which is no longer there, it's a single bond now, gets a hydrogen. Now there are 4 bonds to carbon, so I know how to fill. This first carbon has 1, so I can put in 3 more. Now this carbon has 3 bonds, 2 to carbon, 1 to hydrogen. I can write it this way, H. And this one has 2, 4 minus 2 is 2. Now, on my test, I would recommend leaving it like this. But in real life, the way you draw it would be this carbon has this hydrogen, this one, so it'd be CH2. And this one has these 2 and this one, and it would be CH3. You can draw it this way or this way. I have a piece of paper written, signed by the Board of Regents of Michigan State University, saying I know those are the same, my PhD degree. But on a test, I'll let you do it either way. And I better tell you the following. I am this close to the person who grades my test, me. So when I say you can do it either way, for my students, I'd rather just have the hydrogens coming down, because that's one less step you have to do. So let's look at, how do you do this? You look for what's different. Pi bond, double bond. What are we reacting with? Hydrogen, nickel catalyst. Well, I've got a double bond, hydrogen, a catalyst, and you've memorized this general reaction. You break the pi bond, each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. And therefore, I have 3 carbons I start with. I end up with 3 carbons. But as in my general reaction, I broke the pi bond, So instead of two lines, there's only one, and each carbon of the double bond that we're in the double bond gets a hydrogen. And you can write it this way or this way. And that's how you do it. Andrew, I guess you got kicked off, but you can always come back to the video to pick this up, okay? Let's do another one. Now, one thing I do on here in organic chemistry, it's on a whiteboard all the time, is have an arrow with a bend on it because you're running out of room. And I'll do one more, and then I'm going to share the fun, let you have some fun too. And the question is, give the organic product or products are the following. How do you do that? First of all, I'll give you all a chance to write it down if you'd like to. All right, let's take a look at this. Now, what's the first thing you should do? Look for what's different. What's not carbon or hydrogen atoms or carbon-carbon single bond should get your attention like that. And if I look at this molecule, oh, there's a double bond there. And it's, as soon as I look at the rest of the molecule, this carbon, hydrogen, carbon-carbon single bond, the only thing that's interesting in that molecule is the double bond. What am I reacting with? Hydrogen. What's platinum? A catalyst, which we abbreviate by CAT. And the catalyst can be, in our case, it is platinum or palladium or nickel. And what happens? Remember, there's one pi bond, one sigma bond, and you break the pi bond, and each carbon of the double bond gets a hydrogen. So if we go up to our actual problem here, do you break carbon-carbon single bonds? No. So how many across? 1, 2, 3, 4, 5. So now I'll still end up with 5 carbons. Which 2 carbons were the carbons of the double bond? Notice I broke one of the bonds, the pi bond. So there's only one line there, which is what our general reaction shows us. And what does it tell us? Each of those carbons will get a hydrogen. And now I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And you're done. Now, organic chemists use these general reactions to make molecules. Think of them as building tools. If you think about it, a carpenter knows how to use 1x2s, 2x4s, wood to make things. Well, we use these general reactions to make things. All right, now it's time for you to have some fun. And the question is, give the organic product or products for the following. 3 points each. Your turn. And when you're done, give me a thumbs up. If your camera's on, use your hand thumbs up. Hopefully I'm not dealing with anybody who's missing thumbs. If you are, tell me in private. Or use your emoji. Actually, I knew a chemist who, when he was young, he lived on a farm, was missing part of one of his fingers. Farms can be dangerous places to work. I learned that from, I still remember his first name, Gene. Yeah, I haven't thought about him in decades. Nice guy. I hope he's still alive. Ouch. But anyways, When you're done, give me a thumbs up. I know Andrew's already done. And Christiana is done. And we'll wait for it, Nash. And everybody's done, so I can get to work. How do you do this? You look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your, a double bond. We have a double bond. Nothing else is going to react in that molecule. Reacting with hydrogen. What's palladium? A catalyst. And remember, the catalyst can be platinum. In our case, it's palladium or nickel. And remember, you've got a pi bond and a sigma bond. And you break the pi bond, each carbon of the double bond gets a hydrogen. You break carbon-carbon single bonds? No. So I have 4 here. I better end up with 4 carbons. Now, I do my hydrogens at the very end. It's easiest. Now, notice I broke one of the bonds here, because that's what our general reaction tells us. And each of these 2 carbons gets a hydrogen. And now if I look at the first carbon, there's 1 bond, should be 4, 4 minus 1, 3. The cis carbon, 2 bonds, 4 minus 2, 2. Now this one right here has 3 bonds, 4 minus 3 is 1. And this has 2 bonds, this hydrogen and carbon, 4 minus 2 is 2. And you could write it that way, or you could have written it this way. You don't have to put the lines in, I do. And either way is correct. And let me do this one, and then I'll let you have one to have fun with. And if we look at D, what's different? Oh, we've got a ring, but a ring are just carbon hydrogens and carbon-carbon single bond. Wait a second. Look what we have in the ring here, a double bond. And what are we reacting it with? Hydrogen and nickel as a catalyst. And remember, the catalyst can be platinum, palladium, or nickel. Now, what does the general reaction tell us? You know, learn this. You've memorized this. You break the pi bond. It's also got a sigma bond you don't break. And each carbon of the double bond gets a hydrogen. Well, in a ring, you don't show hydrogens. So I'm going to break the pi bond, and I'm done. Again, in a ring, you don't show hydrogens. Now, let me prove you something to you, and that is, notice here, when you do a hydrogenation, you're adding 1 hydrogen to each carbon of the double bond. Now, if we look at this carbon right here on the ring, how many lines are bonds? 1, 2, 3. 4 minus 3 means it has 1 hydrogen. We just don't show it. Now, if we look at that same carbon in the product, how many hydrogens are on there? That carbon, 1, 2, 4 minus 2, there'd be 2. So you went from 1 to 2, so you did add it, but we don't show that on a ring. And that's just convention organic chemists do. And here's one for you to have fun with. Give the organic product or products for the following reaction. I guess the other reason I'm also happy is with Labor Day and with my teaching schedule, I have Thursday, Friday, Saturday, Sunday, and Monday off. Well, not off, I've got work to do. Plus, I got to go to the dentist tomorrow morning. Ouch. I'm having some oral surgery. Double ouch, even though he's quite good, really good. I mean, really good. I'm lucky I found him through the medical group I go to. I asked, anybody recommend a good dentist? And they told me this person, and they were right. All right, anybody need more time? Don't forget, give me a thumbs up when you're done. Thank you. So what do we look at this problem E, what's different? Thank you, Andrew. What's not a carbon-carbon single bond or carbon-hydrogen atom? Ooh, a double bond. And again, the general reaction, double bond, what are we reacting with? Hydrogen. PT is platinum, which is a catalyst. And remember, there's one sigma, one pi. We break pi bonds to break sigma, which is also known sigma bond, single bonds, no. So I'm not going to break it, but I'll break the pi bond. Each carbon of the double bond gets a hydrogen, and we're done. So do you break carbon-carbon single bonds? No. So you're still going to have the ring. You're still going to have the methyl group on the ring. Ooh, let's take a timeout break. 3 months ago, if I'd said methyl group, would you even know what I was talking about? Some of you might, some of you didn't. See how much you've learned in our short time together? Doesn't that feel good? It should. All right, let's get back to work. So I broke the pi bond. Notice there's only a single bond there, and I'm done because I don't show hydrogens on a ring. That's how you do it. When I first started teaching Chem 170, and I didn't start brainwashing, that's really what I'm doing to you, burning it into your brain, you break carbon-carbon single bonds, students would do the most weird things, and weird meaning always wrong. Remember, your friends on every test will be, how many bonds to carbon? 4. Do you break carbon-carbon single bonds? No. All right. Well, I better let you, you have another chance at this. Did I give you this one to do on your own? Yes, I did. All right, let's do one more. Now, the favorite trick on a organic chemistry exam is to put a big, scary molecule. If you don't know what you're doing, then this is a big, scary molecule. And the question is, give the organic product or products are the following. Or tonight at midnight, did I give my, ooh, I'm going to postpone it till next Wednesday. Yeah, maybe not. I'll postpone it till next Wednesday because I should have sent out an email. Next Wednesday, and somebody, I'll remind myself right now. I'll send out an email. I will teach you how to eliminate test anxiety. And it's helped students in all my chemistry classes for a number of years now. If they have a problem with test anxiety, they usually go from getting D's and F's to getting B's and A's. But I will cut it out of the video, which is why I didn't want to do it today, because I forgot to send out that email. Oh, well. There's plenty of time before the first test. All right, anybody need more? Everybody who's done, give me a thumbs up. All right. Now, if you didn't know how to do these problems, you'd look at that and say, eek. Oh, I don't know if you go eek, but it's a big, scary molecule. But no, if you look for what's different, There's only one thing different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, a double bond. And as soon as I see that and the rest are just carbon, hydrogen, carbon-carbon single bond, boom, I forget about the rest because that's just going to come along for the ride. And if I add hydrogen and a catalyst, which is what nickel is, remember the catalyst can be platinum, palladium, or nickel. If you work in industry, you use nickel because of the price differential. If you work in a pharmaceutical or research in a university, you use platinum or palladium because you don't worry about the price differential. And you break the pi bond. Remember, there's one pi bond. You should know in a double bond, there's one pi bond, one sigma bond. And you should know this. And each carbon double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 across. On this carbon, I have 2 methyls. On this carbon, I have a methyl. And on this carbon, I have a methyl. Notice I didn't break any carbon-carbon single bonds. But between these 2 carbons, which are these 2, I broke the pi bond, because that's what this happens. And each one of those will get a hydrogen. And now I know there are 4 bonds to carbon, and I can put in my hydrogens. And I'll be doing it in warp drive. And I'm done. Now, from today on out, it's your solemn responsibility to let me know if I made a mistake on how many hydrogens a carbon should have. Again, that's your solemn responsibility from here out that I put the right number of hydrogens on carbons, which in that molecule, I believe I did. I think I did. And that's how you do it. Any questions? Again, this is your second general reaction that you need to memorize. A double bond plus hydrogen and catalyst, where the catalyst can be platinum, palladium, or nickel. You break the pi bond, and each carbon to double bond gets a hydrogen. Now, how many of you have heard of hydrogenated fats and oils? Later in the semester, when we get into fats and oils, the fats and oils, or vegetable oils really, have a double bond in the molecule. Guess what? They reacted with hydrogen, break the pi bond, and each carbon gets a hydrogen. Now, why do they do that? Well, I'll teach you later, and you just got to wait. Ooh, a monster 14-week cliffhanger. Maybe, yeah, 13-week. Stay tuned. All right, let's get back to work. Now, the next reaction I'd like to talk about is halogenation. Remember, the halogens are the compounds second to the right column on the periodic table. And for organic chemistry, we're talking about fluorine, chlorine, bromine, or iodine. Now, someone sometime in the long distant past decided we'll abbreviate any halogen by the letter X. Again, X in organic chemistry means halogen. And notice I have fluorine, chlorine, bromine, or iodine. Now, halogen gas is a diatomic gas. It exists as 2 halogen atoms held together. Just like oxygen gas is O2, halogen gas is X2. And here is the new general reaction. Now, I shouldn't have introduced it yet, but notice how I have R prime, S like X and Y in math. This could be one thing, this could be the other, or they could be the same. Here, X and Y could both be the same number or different. Well, we use that. But a better way to learn this reaction is any double bond plus a halogen. You break the pi bond. One carbon gets a halogen and the other one gets a halogen. Remember, X is fluorine, chlorine, bromine, or iodine. And that's the third general reaction you need to know. A double bond reacting with halogen gas, X2, you break the pi bond, and each carbon gets a halogen. Now, good news, you've got an instructor who's worked in the real world in organic chemistry. So I know a lot of stuff that academic chemists don't know. Academic, those who have just worked in academics. And the question you should be asking yourself from here on out is the following question always. Why am I learning this stuff? Well, the obvious answer is, well, someone told you had to take this class to get a good grade to get into a program or a school. That's why you're learning it. Well, why learn organic chemistry? Well, these are things in your daily life that are useful to make molecules that are useful in your daily life. Now, why is it useful to put a halogen, a couple of them or more, on carbons in a molecule? Well, one use is it makes it less flammable. And those molecules with a lot of halogens in them have been used as fire retardants. Now, there's no chemical additive that can make something fireproof. If it can burn, you can heat it up high enough, it will burn. But fire retardant slows down something from burning super fast. It will still burn, but it slows it way down. And where's an important thing you want to slow down from possibly burning? Children's night clothes, pajamas, and or whatever they wear to go to bed. Because if they get too close to a space heater or a candle or a burner in the kitchen, in the old days, their sleepwear was quite flammable, and a lot of children got burned badly. Now they add chemicals, a number of them are halogenated to inhibit them burning. All right, so the general reaction, double bond, halogen, break the pi bond, each carbon of the double bond gets a halogen. So let's take it for a fun spin. And the question would be, give the organic product or products for the following reaction. Well, like I said, from now on, you should look at a molecule. You'll hear me say this over and over again, but it's true. I do. When I look at that molecule, I've scanned it like that. Oh, by the way, I'm a speed reader too, so I can scan things. Do I have time? I do. If I were in lab, you'd find out when I look at certain things you show me, but back in fifth grade, the summer of fifth grade, back when I was in grade school, there was this new experimental program being tested in the United States. And one of the places was at my grade school. And my parents found out about it and said, you should go. And I said, Mom, it's Dad, it's the summer. I don't want to be in school. Well, you can go. And whenever I would fight back, they always had the same answer. all right, if you don't want to, move out. Which as soon as I heard that, I'm going. And this was an experimental speed reading. And it was, at the time, I didn't like it because I was in school during the summer. But years later now, I'm so grateful because I can read fiction at about 100, 120 pages an hour. Scientific, I'll slow down. I slow down to 30 to 50 pages. But anyways, let's get back to work. Now you learned something about Dr. White. So this is a reaction. And let's look at the example. And you have looked at this molecule real quick. I've scanned it. I can scan these real quick. What's different? What's not a carbon or a hydrogen atom or a carbon-carbon single bond? Ooh, a double bond. What are we reacting with? Br2. That's halogen gas, bromine gas, which we show the halogen gas X2. Remember, double bond, one pi bond, one sigma bond. You break the pi bond, one carbon gets the halogen and the other one gets the halogen. Remember, X is the halogens fluorine, chlorine, bromine, or iodine. So, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across. I better end up with 4 across. Now, here's where you have to pay attention. Which carbons were the carbons of the double bond? Because those are the carbons that will get the halogen. And that's these two. And each one gets a halogen. What's X? Bromine. And that counts as one bond to carbon, each one of those. So now I can put in the hydrogens. Let's look at this carbon. 3 bonds, one of those is this bromine, 4 minus 3, 1 hydrogen. Let's look at this carbon. 2 bonds, one of them is bromine, 4 minus 2 is this. And this is called, I'll teach you next chapter when we'll use it more. Bromine as a substituent is a bromo group. And that'd be 1,2-dibromo butane. Now, one other thing I should tell you, very small molecules with halogens on them are very bad carcinogens. Again, very small molecules. This will never be on a test, but it's something to remember the rest of your life. Which reminds me, if you, excuse me, oh, that water is strong. No, but anyways, really smooth. But anyways, if you ever go house hunting, make sure you never buy a house near an old dry cleaner site. Why? The old dry cleaners used to use a solvent, not water, to clean your clothes. And it was a halogenated hydrocarbon, a molecule very small with a lot of halogens on it. Usually it was dichloromethane or maybe chloroform or carbon tetrachloride. All those are very, very bad carcinogens. Well, back in the 40s and 50s, when this was getting started, instead of spending money to have their waste taken away, because you couldn't dump it down the drain, they went across the field from their store and just dumped it into an empty field. So be careful. All right. Oh, the other thing I wanted to mention, watch closely. These are the only 2 carbons those bromines go on. And that's what the general, they have to be adjacent, and they're the 2 carbons of the double bond. And I see this a lot. People get sloppy or just don't know the right answer. And sometimes I'll see this on a test. And what I'll do It's wrong. 0 points, because this bromine should be there, not there. And just like if you were asked to draw a face and you put the nose on the forehead, would you expect to get full credit? No. Or if you put an eye on a chin, no. And you have to be very careful in organic chemistry, because that's just the way it is. That's the actual molecule. This one that I crossed off wrong is different from the one I wrote. Those are separate molecules. They're as different as night and day to an organic chemist. And that's why that's wrong. So pay very close attention where you put new things. All right. Oops. And here's one for you. Give the organic product or products for the following reaction. That was, hold on. There we go. I wanted you to be able to see the general reaction because you haven't memorized these yet. And when you're done, don't forget, thumbs up. All right, time for me to get to work. All right, what's the drill, or what's this? You look at a molecule, look for what's different. It's not a carbon-carbon single bond, carbohydrogen. Ooh, double bond. So there's nothing else will react with the reagent. What's Cl2? That's halogen chlorine gas. By the way, I've worked with chlorine and bromine gas. It's nasty stuff. Got to be really careful, or you can hurt yourself very badly. And the general reaction is react the double bond, which is one pi bond, one sigma bond. You break the pi bond, and each carbon of the double bond gets a halogen. And remember, the halogens can be, in this reaction, fluorine, chlorine, bromine, or iodine, the halogens. And do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. I better end up with 6 across. And then over here, I have a methyl group. That better come along for the ride too. Which are my 2 carbons of the double bond? Here, I've broken 1 of the 5 bonds. And here are my 2 carbons of the double bond that were in this molecule. Now, our general reaction tells us each one gets a halogen. What's our halogen? X is chlorine. And I know there are 4 bonds to carbon. And that's the molecule. And let me do something I can do. Make it a little larger in case anybody could make out. And that's how you do it. Oh, let's do another one. By the way, anybody have any questions? And what would be the product or products for the following reaction? By the way, see how I'm secretly training you how to look at a molecule? Am I sneaky or aren't I? Oh, I better use proper English. Am I not? Oh, my high school English teacher would be smiling now. And remember, when you're done, give me a thumbs up. All right, I think everybody's done, so I better get to work. Ooh, we've got a ring, but a ring is this carbon-carbon single bonds, except I've got a double bond. Everything else is carbon, hydrogen, carbon-carbon single bonds, but double bond, and F2 is fluorine gas. That's a halogen. Remember, X can be, in this case, it is fluorine, chlorine, bromine, or, whoops, not everybody reads cursive, so I better print it out. I guess that's a generation gap. And each carbon of the double bond gets a halogen. Well, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. I'm still going to have my isopropyl group. That's coming along for the ride, and it did. Now, which 2 carbons of the ring were in the double bond? which are these two. And each one will get a halogen. In this case, it's fluorine. Now, you don't have to show the hydrogens on there, so I'm not. And I'm done. And that's how you do halogenation. Oh, let's do one more. I don't want to cheat you or anything. And here's one more for you to have fun. Am I nice or am I nice? Don't answer that. Oh, I really am in a good mood to talk about fun things to nice people. Other things, good things are happening to me. Better shut up or I'll jinx myself. Don't forget the thumbs up. I see one person's done. 2, I'll train you. And it's time for me to get to work. Now, if we look at this molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon single bond should get your attention like this. Hopefully I got your attention. And it's a double bond. And we have a double bond reacting with iodine gas, which is a halogen. And remember, X can be fluorine, chlorine, bromine, or, I did it again, or iodine. I think I'm going to send out an email, teach you all cursive or, nah. And you break the pi bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. Remember, you break the pi bond, but not the sigma bond, single bond. Well, I have 3 carbons across and a methyl group. They're going to come along for the ride. Here are my 2 carbons of the double bond, which are these. Notice I broke one, the pi bond. Each one gets a halogen. In this case, it's iodine. And that counts as a bond. Don't forget there are 4 bonds to carbon. So I can put in the hydrogens. And I'm done. And that's how you do halogenation. And one of the important things, halogenation, is to make things that are fire retardant and also heat resistant. And there are other things I'll teach you later why having a halogen in a molecule is a good thing. If I look at the time, it's time for a break. Oh, maybe a 30 seconds early, but I'll give you an extra long 30-second break besides the 5 minutes. So let's take a 5-minute break and come back at, oh, I'm right on time, 2:50, and then we'll start the lab. So take a 5-minute break. I'll come back and do our lab. Oh no, I'm running late. Time to get moving. Just close that. That I'll keep. All right. It's lab time. And on Wednesdays, we'll have lab, which we're going to have right now. Now, if we were face to face at ECC on Wednesdays, I would normally lecture, except this time I would go a little longer. Maybe not. Anyways, we work it out. For 50 minutes, take a 10-minute break. We take a longer breaks when we're face to face. On this class, you're getting the same face time, this face. Oh, that was bad. Sorry. Anyways, face-to-face time that we would in a classroom. And then we'd have the lab. Now, when I inherited, and that's a good way of putting it, Chem 170, the labs that were being used were, to put it mildly, beyond awful. They were terrible. And one of the problems with the way Chem 170 is set up at ECC, a one semester organic, they only had an hour 50 designated for a lab. At COD and other College of DePage, where I also teach this, have taught the same class called 1212 there, they have 2 hours and 50 minutes. What that means is I couldn't use the normal lab books, because if the lab went over an hour and 50 minutes, I couldn't. So I challenged myself, instead of finding a lab book that would help, I said, I'm going to write all the labs for the whole semester. And I did. So these labs are labs we'll do. Now, what I'm doing now online is you're just not going to manipulate the chemicals. What I will do is the same introduction and teach you the same things for each lab that I would do face to face. You'll get the same labs, but you're just not going to go into lab and get the data. And for this class, it'd be fun, it's nice, but the fact that you can do it online, especially during the pandemic, and in my mind, I don't think it's really over. Dr. White wears a mask whenever I go into supermarket or any stores or things like that, out and about. But anyways, so let's talk about our first lab. Now, before we do that, let me log into D2L. All right, everybody see D2L on your screen? Now, let me do one more thing. Let me go to student view because my interface is slightly different. This is what you would see. Now, notice at the top here, we have content. I never use discussions. We can do that. I don't do quizzes. Grades is a grade book. Class list allows me to send emails to everybody. But if you click on assignments, you'll see the signature sheet and oops, I forgot to do something. Hang on. It's been a busy little time for me. Now you'll get to see the inner workings of D2L. And that's the reason why I thought I did this already. I apologize. Sorry about that. All right. Oh, all right, now let's go back to student. I thought I'd done that. Obviously I didn't. I apologize. All right, now we're in student view. Click on assignments. You'll see lab 1 melting points. Now, what I have here, for those of you who have Microsoft Word, I have it as a Word document. If you don't, I have it as a PDF. You don't want to use a computer, your tablet or cell phone, which you could do, I have it as a PDF. Now, this semester, you'll be doing the labs, and also you'll be taking tests online. And what you'll need to do is, whatever your answers are, you'll need to either scan that. If you don't own a scanner, you will have, I'm sure everybody has access to a cell phone with a camera. And there's 2 ways. If you have a scanner, make a PDF file and you upload it to here. If I were to click on here, let's click on here. Where it says upload, add a file, this is where you'd upload it. And then you click on submit. Now, let's look at these files. Actually, let me go back. I have this, and then I have how to do this. I have 2 different ways of looking at the file. Then, about 2 years ago, a student taught another faculty member who taught me that there's a nice app for your phone called Cam Scammer. And you can take a picture and automatically from that, once you're done taking a picture of all the pages, it automatically, you click on something. I've never really used it because I have a scanner myself, but it will make a PDF file, which you can then upload to here. Cam Scammer is a free paid app. There's a free version and a paid version. Don't waste your money on the paid version. Use the free version, and that's how you'll do it. All right, let's get in today's lab. Everybody see on the screen melting points, Chem 170. Thank you, Dacio. Now, what's a melting point? How many of you have ever seen ice melt? You know, if you have ice cubes in your glass of something, I'll be G-rated, pop or water, or I guess you could have iced coffee or iced tea too. I don't like those, but anyways, what's melting? Melting is when something goes from a solid to a liquid. So melting and I should say, take good notes or come back and watch the video again. Now, organic molecules melt. If they're a solid, they can become a liquid. And the temperature with that happens is called the melting point. Now, organic compounds, unlike inorganic, have a low melting point, below 300 degrees C. If you look at table salt, and I'm guessing now, but table salt has a melting point over 1,000 degrees C. In other words, it's not going to melt in your oven, which is why cooks use that. I've never done it for a salt dome to cook certain things in an oven. That's one way. Now, let's go to my whiteboard. If you have a sample, let's call it compound X. Am I being creative or what? And you take the melting point. How do you find out what is the melting point of compound X? You have a sample that you heat up in a device called a melting point machine. And there are different styles. We have 2 styles that we can use at ECC. And as you're watching this temperature, the sample, as soon as you see any liquid, we call that the start. So say it started, you were heating it, and this started seeing a little droplet at 92 degrees Celsius. And when all the sample is liquid, I can spell liquid. Let's try that again. That's called the finish. And let's say that was 193 degrees C. So what's the melting point of compound X? 92 to 93 degrees C. Now, sometimes that might be more than 1 degree difference, it might be 2, but it's usually quite narrow. It's never 10 or 20 for a compound. So that's melting point. Again, the start is when you see any liquid, and the finish is when the sample is all liquid. Now, the way we do this is we put a small amount in a capillary tube and put it in the device. You have a magnifying glass and you have a controller, and in that machine, you have a heating block. Don't touch that, it's hot, and you'll burn yourself. I warn students when we do this. So again, the first number is when you see any liquid, and when it's all liquid, you're finished. That's the second number. Now, important thing is that when you're taking melting points, you don't want too much sample because it's going to take longer and give you erroneous data, bad data. You try and do the minimum amount of sample to give you the best melting point, because don't forget, you've got to wait until it all melts. And if you have a ton of sample, it's going to take a long time. You're not going to get a good melting point. Also, when you're doing this, melting points require patience. If you heat it up too fast, you're going to zoom right past it and you're going to get an incorrect melting point. Now, what's the reason for taking melting points? Well, chemists use melting points, see it's written right here, to determine identity of an unknown organic molecule. That's one reason. And the other is to determine purity of an organic molecule. So melting points are used to determine either purity of a compound or identity. How do you do identity? Well, there used to be tables, but now you can find it on the internet, the melting point of certain compounds. And let's just show you one in particular. All right, I just want to, everybody see urea Wikipedia on your screen? One of the nice things about Wikipedia for organic molecules, if you look on the right side, scroll down, you'll see properties. Oh, look, melting point, 133 to 135. So if I have a compound that has a melting point of 133 to 135, or it could be 132 to 134, which is very close to it, it could be urea. And that's how we use it. I'll talk more later on about urea when we get into nitrogen compounds. That's in about week 13 or 12, so we got a while to go. So melting point, for you can find these online for various compounds. They actually have ways, and I haven't used it in a long time. Here's a melting point. What are the possible compounds? But anyways, that's how you use it for identity. Now, the other thing is purity. Purity, how can you tell if something's pure? Well, I have to talk about what's called the colligative effect of compounds. You might have learned this in general chemistry. Colligative effect is when you mix two different chemicals together, something happens to their physical properties. For melting points, and I'll write it on the whiteboard, the melting point gets wider and gets lower. If you have two compounds and they have the same melting point, when they're pure, if you mix the two together, the melting point drops. It's called melting point depression, and it gets wider. So if you have a compound and you already know its melting point, if it's not the exact melting point you expect, you know it's not pure. And that's the colligative effect. And we can also use the colligative effect for identity. How do you do that? Well, let's go to my whiteboard. So the colligative effect, when you have two different compounds mixed together, even if they each one have the same melting point alone, the mixture will always be lower and wider melting point. Now, what if you have compound A? But you're not sure what it is, and you think it's compound A, and you have a pure sample of compound A. If you mix the two together, the melting point won't change. Now, if you think it's compound B, it's really A, and if you mix A and B together and you're wrong, the melting point will go lower and wider. And that's how you use the colligative effect. Remember, if two different things are mixed together, the melting point will go lower and wider. And if you're trying to identify something and you think an unknown is this compound, and you mix the known compound with the unknown, if the melting point stays the same, then you know the identity. If it's not, you don't know it yet. So let's take a look at today's lab. Now, here's a video I'll let you watch on your own, especially at 5 minutes, 42 seconds near the end, to the end. Start there, and I'll show you how you do a melting point. Now, here's a procedure. You usually put it in a fine powder. The ones we use for this class have a capillary tube, very thin tube. You take it and pretend this is a capillary tube. which means this end is open, this is closed. You stick it this way into the sample, get a little in there, then on a hard surface, you tap it down and it'll go right to the bottom. You only want a little bit. You don't want to fill the whole thing because that's going to take longer to melt and give you a bad melting point. Oh, I should point out, for my PhD thesis, I had to do the melting point of new products that I made, and there are over 100. So, and I did each one 3 times. It was for my thesis. All right, and then you'll put it in there. You'll slowly heat it. And when the first liquid appears, that's the starting point. And then when it's all liquid, that's the finish. And you'll repeat this for some unknowns. Now, everybody see results on your screen? In the lab, if we were doing it, you would actually do the melting points, but I can't have you do this. Now, one of the nice things about this lab, if we're doing it face-to-face, and you just got to trust me, I'm giving you the right data, is you can find out if I'm lying to you or not. And that's the beauty of all science. You go in the lab and prove things. Now, notice urea and trans-cinnamonic acid have the same melting point. And what happens when you do a 50-50 mixture? It goes way down and way wider. And that's the colligative effect. So you would have had the experience. Now, since you haven't done the, I don't know, hundreds and hundreds, I don't know, over 1,000 melting points, if not more, that I've done, your melting points are not going to be the same as the literature value. Literature value is the value everybody accepts for melting point for a compound. Yours is going to be a little lower and a little wider. Again, in real life, and I have done that in this table. Now, here's the fun part. Besides you having done these melting points, we also have an unknown. And the unknown, you have to determine what it is. How do you do that? You take and do the melting point. Now, I've given you the data. Watch closely. If you react it with, mix it with benzoic acid, here's the melting point. If you mixed it with cinnamic, and that's actually should be trans-cinnamic, here's the melting point. And based on this data, you should be able to identify what is the organic compound. Now, when we do the lab, you have to determine what to mix. How do you do that? I give you this chart and tell you your unknown is one of those 4 compounds, and you identify it by melting point. Now, since you're not going to do melting points at home, I've given you the data up here. And if you notice, after this, I have questions. And these are what you need to fill out. And then you'll submit this by uploading it to D2L. You don't have to hand in tables pages 1 through 3 unless you want to. And on page 4, you have to put in the identity of what you think the unknown is. And I just gave you the information how to do that. And you have to answer these questions. Well, you don't have to, but if you want your 11 points, you do. And this is due by next Wednesday, end of the day, for you to upload it. So you have a whole week to finish it. And that's the lab. Any questions? Going once, going twice. All right, let me remind you, next Monday, because it's Labor Day, there's no class and there's no office hour. Next Monday, again, no class, no office hour. Another thing I'd like to talk about, and I think I mentioned earlier, I think I did, if not, I'll mention it now, and that is my office hour the best for you? And I'll keep it on Monday and Wednesday. I may change it to Tuesday if people want it. But on Monday and Wednesdays from 9 until 11, I'm tied up with a class I'm teaching at COD, so I can't do it then. But right now I have it from 5 to 6:15. If you'd like me to do it a little later and go to the same hour and 50 minutes on Monday and Wednesday, let me know and I can change it. So send me an email if that's it. And with that, don't forget, keep on working on the practice problems. And I'll see you next Wednesday. Next Wednesday, we'll do lab number 2. And that's the, I think it's the alkanes and alkenes lab. And with that, have a happy Labor Day long weekend. Have a happy rest of the week. And unless you're coming to my office hour tonight, I'll see you on Wednesday. And with that, I'll say, Kein Gesund, goodbye. Remember, I stole that from Granny and the Beverly Hillbillies. Kein Gesund is Yiddish for going out. Kein Gesund, goodbye.